Herein you'll find simulation results and lots of math. We're excited for you to join us. The first item we were tasked with was gathering performance data on a DAC ADC circuit on a local board and comparing those results to a similar experiment run on a remote system. Our results come from two distinct chips, 15 for the local, 13 for the remote, but remain effectively the same. As you can see, the input and output are roughly aligned until about 1.8 volts, at which point they diverge. This is likely due to the loading effects present in the switches in the FPAA. The NFET simulation data, seen here as a red dashed line, lines up excellently with the data from the golden FET, which is represented by the blue circles. Data to the left of this plot was limited by measurement sensitivity and was omitted from the threshold region. We extracted I0 from the above threshold region, the threshold voltage, and the threshold current. From a glance, the threshold voltage here is around half a volt, which means the threshold current is about 19.5 nanoamps. This matches the calculated data fairly well. To obtain the threshold voltage for the NFET, we used the drain current equation shown here. We were able to simplify it by assuming the device was in saturation and that the source voltage was at 0, which makes sense because we're doing an NFET gate sweep. That allowed us to get it into this form here. Using the values obtained from the MATLAB curve fit in the saturation region, shown here, we then were able to figure out that the threshold voltage algebraically is about 0.99 volts, which matches up with the data that we were given. The kappa and VTO we ultimately used to run the simulation were very close to our calculated values. One thing to note is that the subthreshold and above threshold curve fits are nearly perfect, but the simulation has a slight positive offset. Here we see our PFET gate sweep simulation data in the red, which we use to represent all of our simulations. The curve fits are in the black, and the data actually given to us is in the blue circles. As expected, this graph is a horizontal mirror of the NFET sweep. This data has slightly more error than the NFET. The main concern was that our calculated kappa value was too low to match the data. While this gave a reasonable match subthreshold, the above threshold simulation results were less than desirable. Strangely, the threshold voltage appears from the graph to be around 0.6 volts, but the above threshold fit gave a threshold voltage of about 0.48 volts. For the source sweep, the gate and drain were both held at VDD, causing the device to always be in saturation. Again, current above 2 volts was too low to be measured accurately. From the above threshold region, we extracted the slope. Combining this fit with the gate sweep gave us K and kappa. As the source voltage increased, it eventually exceeded kappa times VG minus VT0, causing the device to go sub-threshold. In this region, the slope of the fit gave us the thermal voltage. The calculated thermal voltage of about 30 millivolts was higher than expected. Our initial simulation using this value did not fit the data well. We also combined and calculated the thermal voltage with the gate sweep results to give an accurate kappa value. Interestingly, this gave a kappa of about 0.37, which was way low. In addition, the kappa calculated sub-threshold was significantly lower than the kappa calculated above threshold. When performing the sweep, we chose kappa in between these two values to minimize the mean square error. As with the NFET, the fit of the sub-threshold data here gave a thermal voltage of around 29 millivolts. This turned out to be too high, and the simulation again did not match the data well. We wound up simulating with a lower thermal voltage to get a better match. The K value for the PFET was lower than the NFET based on the above threshold data. This was expected, as typically holes have a lower mobility than electrons. Here we see the NFET drain sweep with the device operating in sub-threshold mode. We can tell we are in sub-threshold operation because we enter our saturation region here at around 100 millivolts, and the saturation current is a rather low value of 38.3 nanoamps. We see the device quickly exits ohmic operation and enters saturation mode, and both the simulated data in red and the fit data in black line up very well with this performance. Based on the slope in the saturation region, the early voltage is 26.9 volts, giving a sigma of about 0.0011. As for the NFET, the PFET current saturated at about 100 millivolts. This indicated the device was sub-threshold. A low saturation current reinforced this observation. As you can see, it's only about 9.74 nanoamps. In the saturated region, we determined the early voltage to be 9.26 volts with a sigma of about 0.0032. Here you can see the values we calculated for each device type. for the PFET here and for the NFET here. We found that the calculated values did not generate very good matches in some cases for the data. Primarily, we found thermal voltage to be too high and kappa values to be too low. Additionally, we found that different values of kappa gave better fits in different regions and adjusted it to balance it between the ohmic saturation and sub-above threshold regions. The NFET, our calculated threshold voltage, was actually a good fit. However, it turned out the thermal voltage of 30 millivolts caused the slope in the sub-threshold region to be too low. We also found the source sweep to be different in regards to kappa. Based on the drain sweep, we calculated value of sigma was too low, e.g. the DI-BL effect was stronger than calculated. For the PFET, our calculated sub-threshold voltage was too low. Going back to the gate sweep, this can be seen from the plot, which indicates the sub-threshold voltage of about 0.7 volts below DDD. Our underestimated threshold voltage caused our threshold current to be correspondingly low, as you can see here. Interestingly, a high thermal voltage of 29 millivolts fit the data very well. It is also of interest to compare the NFET and the PFET. The biggest thing to note is the much lower conductance constant K for the PFET than for the NFET. Thus, this threshold current is much, much, much lower. Thank you all for watching. I hope you have a wonderful class and a wonderful day.